Okay, let's start. So last time we entered chapter 4, and chapter 4 is classification. And we studied logistic regression last time. And today we wanna cover the linear discriminant analysis and the quadratic discriminant analysis and KNN. And the methods are in some sense similar, and in some sense it's different. For example, the logistic regression. Logistic regression is represented by the equation. You can see. Yeah. So basically, the logistic regression models the relationship between the response and the predictor as this. And this is a linear model. So basically, we are thinking about some predictor space, for example, x1 and x2 here. And we have y values. So maybe some observations are in group 1 and some other observations are group 2. And the separation between these two groups may not be perfect. So maybe some observation like this. But we have some tendency that the circles are upper right region of this space and the crosses are more lower left regions. So basically the logistic regression, what we did is actually that we think about some direction defined by beta naught plus beta 1 x. X is in general multivariate vector. So suppose x1, x2, then basically what we are doing is we think about the direction like this. And if the observations the projected on this line has larger score, then observations are more likely to be circles. And if the score on this direction is lower, for example, suppose score 0 is here and -1, -2, and +1, +2, and so on. Then if score is lower, then probability of being a circle is lower. So that is basically what logistic regression does. And the linear discriminant, okay, so basically we have boundary like this. So this boundary is the point, the line, on which the probability of being the group of circles is equal to 0.5. So boundary. So in this sense, the logistic regression has a linear boundary. And today we study LDA and QDA. These are different parametric methods. And LDA also, the boundary is linear. And QDA is the method in which the boundaries are not linear. But the LDA and the QDA have similar ideas. So in some sense, logistic regression and LDA are similar. And in some sense, LDA and QDA are similar. And also KNN is a totally different method. This is more non-parametric method. So we want to discuss this. Yeah, so today's topic is the LDA, QDA, KNN, as well as how to evaluate the fit of the model. So we study sensitivity, specificity, receiver operating curve, and the type 1 error, type 2 error that we cover those things. Probably if you have taken 6840, then you have already studied the receiver operating curve. And if you have taken statistics course, then maybe you have already studied type 1 error, type 2 error, but we cover those. Yeah, so the main topic is basically linear discriminant analysis and quadratic discriminant analysis today. Okay, so last time we have almost finished the logistic regression, but just that we left one slide, so that is this one. So logistic regression, assume the logistic curve. So that is, suppose we only have the one predictor, or just X is a linear combination of predictors, then relationship between X and Y is given by logistic curve. So maybe, okay, so some shift at the center of the curve, but still we have some curve symmetric with respect to this point, and the probability is between 0 and 1, and this curve has a specific shape. So if Y is equal to the phi of X, then basically the phi of X is equal to so 1 over 1 plus e to the power the negative beta naught plus minus beta 1 X. But why this curve is used? So we don't have any specific reason. And the one reason is that if we think about the just standardized version, 1 over 1 plus e to the power negative X, then actually the inverse function is very simple function of log of y over 1 minus y. So that is one reason. But and also another reason is that when we construct maximum likelihood function, that function is concave, so it's easy to optimize. So that is the two main reasons. But other than that, we don't have any other solid reasons to use this logistic curve. Sometimes logistic curve doesn't fit well for the data. I think the most common problem is the tail probability. So suppose X value is -10 or something. So then fitted probability is very small. For example, 0.000001 or something like that. But sometimes because of some reasons, the observations are here. And suppose all other points fit well. All other data points fit well with this curve, but just we have one outlier, and it's not the recording mistake, and actually there is one outlier here. So in such a case, this breaks everything, right? So the likelihood function is product of likelihoods for observations. So even if we have 100 observations and for most observations, likelihood is very high, but finally, if we multiply 0.000001, then it breaks everything. So basically, logistic regression is weak against this kind of outliers. So sometimes we want to avoid that one. And so sometimes, the logistic regression is not heavy-tailed enough. So in such a case, we use sometimes coset distribution. Probably the coset link. So link is the function of this phi of X, and the phi of X is usually the logit function or logistic function, but sometimes we use coset function. Coset function is the cumulative distribution function of Cauchy distribution. Cauchy distribution is very heavy-tailed distribution. So yeah. So basically 1 plus x squared over 1, we can say.
Dr. Shinki?
Yeah.
Just in my head, I didn't do the math, so I can't really say it. is a logistic function minus infinity equal to 1?
Logistic regression minus negative infinity is equal to 0, right?
Yeah, well, when you integrate, or sorry, if we were...
Oh, integrate, yes. You mean this one? This limit is 1, yes.
Yeah, okay, it is 1.
Yeah, so logistic regression is one cumulative distribution function. So you can consider corresponding density function as well. Yes. Yeah, so logistic regression goes to 0 as x goes to negative infinity, goes to 1 as x goes to positive infinity. So the Cauchy distribution, Cauchy function has similar shape as logistic regression. So still for negative infinity, it goes to 0 and x goes to positive infinity. The value goes to 1. And that's the same. And also this is symmetric function. So basically the Cauchy link function is negative infinity to t this dx. So this is the CDF. This is the CDF of Cauchy distribution, and that is called Cauchy function. And sometimes we use this, and this is very heavy-tailed function. So actually, even expectation does not exist. So this function is more robust against outliers. And another popular choice is the probit link or probit function. So probit function is the CDF of normal distribution. So you can see the, as mentioned, the logistic regression is one CDF. So it satisfies the condition of CDF. So CDF is the probability function of some random variable. So this is the CDF. So CDF, maybe if we want to make it as a function of x, then yeah. So this function is a CDF. Right? And if we consider CDF, the most natural choice is normal CDF because normal distribution is the most fundamental distribution. So sometimes the people use the probit link. But the probit link, actually the tail is even lighter than logistic function. So that means as x goes to infinity, it converges to 1 faster for probit function. So actually it is not strong, not robust against outliers. So for that purpose, the probit model isn't good, but the CDF of normal distribution is very natural choice. So we have some extension of logistic regression to bivariate response variable. That is, we have the two dimensions of response. The both are 0, 1. But for example, response variable is whether patient has hypertension or not, or patient has a cancer or not. We have two response variables. So in such a case, we have to consider the joint distribution of the two response variables. So in such a case, the normal distribution is a better choice because the jointly normal distribution is the easier to define compared to t distribution. So for that reason, sometimes we use probit link. So we have some other choices. But in this definition of phi, the phi inverse is not an analytic function. And also the Cauchy link, probably it's slightly easier, but still not as convenient as the logit function. So mostly people use the logit function. Yeah, so some people use even asymmetric distribution such as complementary log-log. And also today's colloquium speaker mentioned another distribution. He didn't even remember the name, but he said some function starting with Q is popular among economists. So there are several choices, but the logistic logistic function is the most popular function to use. Okay, so now that we go to the linear discriminant analysis. So how many of you have heard of linear discriminant analysis? Maybe all of them. Oh, okay. Maybe most of them. How about James? Luke? Ryan?
I've heard them before.
Ron? No. Okay, so then it's good to explain it. And okay, so for logistic, the LDA, linear discriminant analysis, is a kind of similar method to logistic regression, but it has some strengths. And the one strength is stability. So LDA is more stable than logistic regression. And the logistic regression is unstable when classes are well separated in the predictor space. So this is a kind of contradictive, right? Because if two groups are separated easily, then of course it's easier to estimate the model. But in case of logistic regression, it's not true. And actually, if we have more noise, that means that we have overlap of two groups. Logistic regression is more stable. So that is a little bit contradictive, but I will explain why. So suppose that we have the two predictors, x1 and x2. And as mentioned, logistic regression is basically based on the linear function of x1 and x2. So basically, we have, p of y is equal to 1 given x is given by some function phi of beta naught plus beta 1 x1 plus the beta 2 x2. Here I write b0 plus b1 x1 plus b2 x2. So basically, logistic regression probability is determined by linear function of this. So as I mentioned earlier, if we have two classes, maybe one class is here and another class is here, then basically it assigns probability based on the score along some direction. So we are fitting maybe just for explanation purpose, I write line here. Okay. And so maybe around here probability is 50%. And in general, okay, so if we put some probability axis, okay, so this is the probability of y is equal to 0, y is equal to 1. So here, maybe I would say that this is 1. And these are zeros. Then probability of y is equal to 1 is calculated as this. So this means that suppose that we have some observation, then we project this observation to this direction. Then we see the score. Then we transform this score by this logistic function. Then we can calculate probability. For example, this is 0.8. Then probability that this point being in the class of 1 is equal to 80%. So this is what logistic regression do. And the important thing is to determine this direction. And the second, how to fit this curve, how to fit this curve. But obviously, in this case, okay, so in this case, two groups are separated. So we have the many lines to perfectly separate these two groups. For example, this line perfectly separates two groups, and also this line perfectly separates these two groups, and also this line perfectly separates these groups, or even parallel. Maybe this one is also fine, and maybe this one is also fine, and so on. So that means the line is not unique. So that means this direction, you can see the beta 1, beta 2, B1, B2. So this direction isn't really stable. And also the parallel shift doesn't make any difference. So that makes B0 also unstable. Yeah, so actually I wrote the logistic curve here, but in this case, the separation is perfect. So probably this is not really the logistic curve, and exact logistic curve should be very steep. So that means, okay, so here almost 0, then suddenly probability goes up and almost becomes 1 immediately. Then this. Okay. So that means the size of B0, B1, and B2 is really large. So as X1 and X2 changes a little bit, then probability dramatically changes. I mean, to be exact, the quantity within this function phi dramatically changes. So we can see that if cases are separable, so these two groups are separable, B1 and B2 are unstable, B0 is also unstable, and also these B0, B1, B2 are all large numbers. So that isn't really good in estimation. So we want to see more stable and the moderate size, the B0 and B1 and B2. But the logistic regression, we have trouble with this. And actually, if we have more noise, more overlap between groups, logistic regression works fine, but this is one weakness. Yeah, for prediction purpose, still it's fine in many cases, but at least estimation has some trouble. And LDA has better way to classify this. And LDA's idea is like this. I think most simply like this. So when we have observed the two groups, and now that we only have the one predictor X, and here the Y is equal to 1, and here Y is equal to 0. Okay? Then green group and the purple group. And based on this data, that we fit the normal distribution for each. Then the green curve and the purple curve are obtained. Then you can see that at this point, so this is X. At this point, the purple and the green have the same likelihood. So we can say the 50-50. So probability of Y is equal to 1 is equal to 50%. And the probability of Y is equal to 0 is also 50%. Maybe around here, the purple probability is much larger than the green one. So maybe 80% and 20%. Maybe here, maybe 90 to 10. Maybe here, green one is almost 0. So 100% purple and 0% green, almost 0% green. So this is the idea. And obviously, for this method, if two groups are separated, then that's much better than not separated. So just the separable case is better for linear discriminant analysis. So in some sense, it's more natural, the methods to classify two groups. Yeah, but we have some mathematics there, so I will explain one by one. And another benefit of LDA is this method is more natural when there are more than two classes. So suppose we have 3 classes, then we can just fit a normal curve for each, the class. And maybe if we only have one X, maybe it's a little harder to distinguish three groups. But if we have the two-dimensional space, it's not difficult to distinguish three groups. So X1, X2, then we have three groups, maybe red groups and the blue groups and the black groups, black group. So these three groups, then it's pretty natural to calculate the center of each group. So this group and this group and this group. Then yeah, we will explain. I will explain later, but we can fit the bivariate normal curve for this. So it's easier to extend the model to a classification of more than two classes. So this is another benefit of LDA. So idea of LDA is estimate the distribution of predictor X for each class as a normal distribution. And then finally, we want to calculate the probability. So given new data points, maybe I should say, okay, so we are not sure this observation, so which group this observation belongs to. So we have to calculate the probability of this point is being the black group or red group or blue group. So we want to calculate those three probabilities. And to calculate those probabilities, we use the Bayes theorem to calculate it. Yeah, I will see later in the example. And the example. Okay, so suppose we want to classify animals into horses, giraffes, and deer by weight, height, and neck length. Yeah. So obviously, the prior information also matters. For example, if you see something similar to giraffes in Michigan, then probably still you believe that is deer because no giraffes, wild giraffes in Michigan. So we have some prior information. Prior information also matters. But okay, so just for now, we just ignore it and approximate the joint distribution of the weight, height, and the neck length of each species. So, for example, the giraffes have longer neck. So, compared to the height. Yeah, and also maybe giraffes have generally higher than the other animals. Or horse, I don't know, horse and deer. I don't know how to distinguish it, but maybe deer has the shorter neck, right? Shorter neck. Yeah. Maybe the total size is different, maybe, which is heavy. I don't know. So with these the variables, I would say X1, X2, X3, that we can distinguish these three classes. And usually it's natural to think about, for example, the weight distribution of giraffes and the weight distribution of horses and weight distribution of deer. But the other way around is a little bit unnatural estimation. So given weight or given height, then what's the probability that animal is being horse? What's the probability that animal is the giraffe? So that is calculated by Bayes rule. Bayes rule is basically the probability formula to flip the relationship between X and Y. So given species, think about the given species, the distribution of weight or height, that is pretty natural concept, but the other way around is not really natural. So just we use the Bayes theorem to flip that relationship. So that is the idea. Yeah, so Bayes theorem is here. So Bayes theorem is just the elementary theorem that the probability of A given B is equal to probability of A times probability B given A time over probability of B. So basically probability of A given B is equal to probability of A intersection B over probability of B. So just we use this rule to prove this. You can see that this one is, so this one is probability of A intersection B over probability of A. So if probability A cancels here and here, then we can see this is P of A intersection B over P over B. So this is this. Okay. Then you can see this and this are flipped. So as long as we have probability of B given A, we can calculate probability of A given B. So that is the Bayes theorem. So now here is the way to calculate the fitted probability. Okay. So you can remember that this one. So for given new data points, we can calculate probability of. So this point being black and this point being blue, maybe it should be this side, and the probability of this point is red. So we can calculate these probabilities, and we want to calculate this formula. Okay, so how to calculate the formula? Here it is. So suppose that the f sub k of x is the distribution of predictor x given a class k. So think about just the height distribution of giraffes, height distribution of deer, and height distribution of horses. So those are f sub 1x, f sub 2x, and f sub 3x. Suppose that is given. And also we know the prior probability. Unconditionally, what's the probability of y is equal to 1 and the probability of y is equal to 2, probability of y is equal to 3. So maybe suppose this is deer, horse, and giraffe in Michigan. Maybe the probability is 99% here, and here maybe 0.0099%, and this is 0.00 maybe 0.01 or something like that. So the prior probability, given no information, still we have the population size. So this, for example. Yeah, so these are given by the pi sub k, pi 1, pi 2, pi 3. And then probability of, for example, the animal is deer given height, height is calculated by this. Yeah, at first, by definition of conditional probability, this is y is equal to k and x is equal to x, and the denominator is probability of x is equal to x. And then numerator, we can decompose it into this. Generally, P of AB is P of A times P of B given A. Right? So then we can transform in this way. And the numerator, sorry, the denominator. So denominator is basically the sum of these. So x is equal to x, but we only have 3 kinds of y. Y is equal to 1, y is equal to 2, y is equal to 3. So that means that this one, at first, we just rewrite this as the case, maybe L is equal to 1 to k. In our case, L is equal to 1 to 3. P of x is equal to x and y is equal to L. Then each term can be decomposed as this. So in total, we have this. So in short, the P of y is equal to L is denoted as pi L. So pi L FL X. This is FL, F sub L of X. So we can write in this way. So this is the formula to calculate these probabilities. So basically we are comparing the likelihood. So likelihood is, for example, likelihoods are 0.8 and 0.3 and 0.9. Then we can see, probabilities are 15% and the maybe 40% and 45%. Likelihood for class 1, 2, 3 are given by 0.8, 0.3, 0.9. Then we can calculate the conditional probability as this. Yeah. Yeah. Have you studied Bayes formula somewhere else? I think it really depends on depends on what courses you have taken. I forgot whether or not I covered in Mass 5700. Yeah.
Yes, you did.
Oh, I did. Okay, great. Maybe 2210. 2210 may not have covered it. Yeah, maybe statistics 5800. Maybe it covers also. Yeah. So now that okay, so this is a kind of the general derivation of probability. So just we have more concrete the discussion here. So suppose that X is one-dimensional predictor. So for example, only weight is available for animals. And suppose that F sub k is Gaussian, so normal. Gaussian and normal have the same meaning. Then F sub k is given by this. So this is normal distribution with mean mu sub k and the variance sigma k square. And here the key assumption. So LDA basically fit F sub kx for each x, but the sigma k, we assume all sigma k's are the same. So variances are the same. So this is a strong assumption. So if you use original scale of the weight, we have the same variance for deer and the horses and the giraffes in terms of weight distribution. We can, of course, change the scale. Maybe we can take log of weight, then just the same scale in terms of ratio. So we can modify it, but still, this is a strong assumption that all groups have the same variance. So this is a key assumption in LDA. So then P sub k is, as seen in the last slide, we can calculate in this way. We can just plug in. So this was originally F sub k of X. Okay. So F sub k becomes this. I mean, F sub k times pi k. Yeah, and sigma is in common. So everything, the same sigma. Even though we take summation of L is equal to 1 to k, the same sigma. So then based on this P1 to Pk, in our case, P1 to P3, we can calculate the probabilities. So these are the probability of deer, horse, and giraffe, given the weight. And now we think about where is the boundary? So just to simplify the situation, we only have two animals, and we only have one-dimensional X. Then what's the boundary? And as emergent, the boundary is the midpoint between mu1 and mu2. So you can see that I think this is actually Yeah, I mean, if pi1 and pi2 are equal, so we need this assumption. But if pi1 and is equal to pi2, then these are the yeah, so these are the so this point is the midpoint. You can see that we have two distribution, one centered at mu1 and the other centered at mu2. Then the boundary is the midpoint, so here. So basically, if the value is larger than this, then the animal is grouped in the group 2, and if smaller, then probability for G1, the group 1 is larger. Yeah, and that can be derived by this. So the delta of x, delta sub k of x is here. This is just the logarithm of f sub k of x, and we can solve the boundary problem. So delta 1 of x is equal to delta 2 of x. So this gives the 50%, 50-50 the probability boundary. So that is actually, okay, so first term cancels, 1 over 2 sigma cancels, and x minus mu k square, but the x square is cancels, x squares cancel on both sides, then only remaining term is the 2 times mu k times x and also mu k square. Right? So then we can simplify it, and x is equal to mu1 plus mu2 over 2. So it's pretty simple boundary here. Yeah. Yeah. So that's the case. And yeah, this is the explanation for this. So the green one and the purple one, that we have the same probability, same normal distribution with the same sigma, and the boundary is just the center. So you can see the peak here is about maybe negative 1.5. Peak here is 1.5. Then this midpoint, the x is equal to 0, gives the 50-50 probability. So original data is like this. So we have some difference between, for example, this being actually the larger probability for purple, but this is parametric estimation. So once you fit the two normal curves, then center is here, 0. And how to estimate this mu k and the sigma? Mu k and the sigma. Mu k should be calculated based on the all x values in class k, and the sigma should be calculated by all observations over all classes. And the mu k is actually the class mean, so group mean. And the sigma square is so-called the pooled variance. So basically the variance of each group, but we take the average of these again. Yeah, so basically this is pooled variance. So so we can estimate mu k hat and sigma hat in this way. Okay, so maybe we will have the 3 minutes break. I think that I found that concentrate on the class for 75 minutes is too hard. Do you have any comments?
At this time.
At this time. Does any of you attend did any of you attend today's seminar colloquium? No? No. Yeah, maybe I will explain that. Maybe this is almost part of lecture, but the colloquium speaker, Timothy O'Brien from the Loyola University of Chicago, discussed the design problem. So design problem is the how to choose X in regression analysis. And think about linear regression. Sorry. So suppose that the linear regression, we have X. So suppose we only have one variable. And then we have Y. And you can determine the X values of the observations. So basically you are doing some experiments. For example, we prescribe drug to all patients and we can just control the amount of drug. And suppose the possible range is from maybe 50 to 100. Okay. And we fit the linear model. Y is equal to A plus BX. And suppose that we can choose 10 observations and we want to estimate the slope as accurate as possible. I mean, that we want to estimate A and B as accurate as possible. So our assumption is that the Y is A plus BX plus epsilon. Epsilon follows normal distribution, 0 sigma square is unknown, and N is equal to 10. We can choose any observations. So for example, 10 observations in equal interval, for example. And then you can choose any X values for these 10 observations. What's the optimal way to choose X values? Yeah. And the answer, to answer first, actually the 5 observation at minimum value, 5 observation at maximum value. So that is the optimal way. And so observation is like this. It's natural because if the observations are all concentrated between, for example, 70 and 72, it's very hard to estimate slope. And also it's very hard to estimate intercept as well, right? But if suppose that the possible X range is 50 to 100 and just 5 observations each, then we maximize the variance of X. And actually we can mathematically derive that if we maximize sum of xi minus x bar square, I is equal to 1 to 10, then the variance of A and variance of B, in some sense, that it's weighted average of variance of A and B. So this is minimized. Actually, the variance of B is minimized and A is also minimized. So then we can estimate this. And yeah, so this is the famous result for models. So, but this is only true if we know that this linear model is correct. If quadratic term matters or a different curve fits better, it's a different situation. But in this case, it's true. And he then discussed the logistic regression case. Logistic regression, we have X values like the -10 to 10. And okay, so suppose the possible range is -10 to 10. Then to estimate the logistic curve, like this. Sorry, maybe. What's the best point to fit? And actually in this case, as we can imagine, not necessarily -10, 10, 5 observations each. This isn't really the optimal design points, because obviously this is a kind of, trivial experiments. For example, we give some poison to 10 patients, and at one hand we give the poison, and on the other hand, then we gave huge amount of poison. Then 5 people arrive and 5 people die. And that is very trivial consequence. And we cannot really estimate this curve well. And he said that if we calculate the variance, how to we calculate how to minimize the variance of estimates, then we can find that the optimal point is quantile point of 17.6% and the 82.4%. Yeah. So that means, yeah, we should know the curve, but suppose that this point is 0.176 and this point is 0.824. And if we use 5 observations here and 5 observations here, then this is optimal design points. So we can estimate it pretty well. So if you want to do experiments, choose X value that you expect 20% of the experiments fails, and another point, 80% of experiments fail or success. Then if we choose those two, to be exact, 17.6% and 82.4%, then you can most accurately estimate this logistic curve. Then he moves on on the case that when logistic regression does not really apply and the truth is more complicated, what's the optimal points? So he discussed that. Yeah. I think it's pretty interesting. Sorry, maybe I talked more than 3 minutes. Yeah, so design is really one topic in data analysis, especially in automobile industry and so on. In agricultural experiments, also biomedical experiments. So I'm not on the design side. So I originally worked for the bank and analyzed the economic data and no experiments in economics, macroeconomics. So I'm not really familiar with it, but the design is important and interesting. Yeah. Okay, so now we go back to the linear discriminant analysis. So, okay, so when X is p-dimensional, what will happen? So in the last slide, the X is one-dimensional, but what if we have the p-dimensional case? Then LDA is done in the same way as one-dimensional case, but we have to use the multivariate normal distribution. And what is the multivariate normal distribution? Okay, so we think about just the bivariate case because other cases are almost the same. Okay, so bivariate normal distribution. This is the bivariate version. Okay, so if we take the section of x1 is equal to k or xt is equal to k, then we can see actually the normal curve here. And it's really the bell-shaped in a real sense. So the elementary textbook says the normal distribution is bell-shaped, but that if it's one-dimensional, that is a kind of picture of bell-shaped. Yeah, and also if x1 and x2 are correlated, then we have this kind of shape. Okay, so yeah, you can see that if x1 gets larger, x2 is also is likely to be larger. Yes. Then to be exact, the bivariate or multivariate normal distribution is given by this formula. So it's a kind of familiar one, as we have already seen that we have already known that the univariate, the normal density. So we have the p-dimensional. So naturally, the 2 pi to the power p over 2. And the sigma square was there for univariate case, but here the sigma is p by p matrix. And we have the inverse of sigma here. So for example, 2-dimensional, 2 by 2 matrix. And this is determinant of sigma and to the power 1/2. This is a positive number. And here x is the vector. So for example, x1, x2, if bivariate case. Mu is also a vector, mu1, mu2. And then negative 1/2 is the same and exponential is the same. Yeah. And here again, that we assume that the pi's are similar, the pi's are the same. So P1, Pi is equal to Pj for all ij. And we assume that the fkx has the same variance. So that means this variance matrix sigma does not depend on k. So sigma may be, matrix. This is a correlation matrix. So the off-diagonal parts may not be 0. So sigma is any basically positive definite matrix. But this sigma is common for all k's. And the mu k is, of course, depends on the group k. And this is the center of the observations in group k. So then f sub k is this. Then you can see f sub k is here. So log of f sub k is equal to this. So this is simpler because the exponential part disappears. And this part we have some term, but this does not depend on x, right? So just that we put this as a constant with respect to x. Also, this part does not depend on mu k either, mu sub k either. So it only depends on sigma and some constants. Maybe p, but the p is anyway constant. Yeah, so then we consider the decision boundary. So when probability of group K and the probability of group L are the same. And actually the P delta K of X and the delta L of X are the same when, so these delta Ks are the same. But you can see that this part, this first term does not depend on K. Only mu K depends on K. So only second term and third term matters. And the last term also does not matter. So only this term and this term are important. So delta K is equal to delta L. That turns out to be this. And you can see this is actually linear function of X, right? Because this is just the linear term of X. This is linear term of X, and others are just constant. We estimate mu K, we estimate mu L, but finally these are just numbers. So this is just the equation of X. If X is two-dimensional, this is equation of X1 and X2. So that means the decision boundary is linear. Maybe you have an assumption that the mu, so pi sub k are all the same, but assuming that actually that this gives linear boundary. And even mu k's are different still. I think the boundary is linear. So boundaries slightly have different shape, but suppose that the f sub k is like this, and that we multiply this by pi k. And then we take logarithm. Right? So we have the plus pi k. But the pi k is a constant. Okay. So pi k is a constant. So finally, we have slightly different curve. So we have pi k. Maybe I should have maybe log of pi k, log of pi k. So plus log of pi k and plus log of pi l. Okay. But finally, these are anyway constants. So it shifts the boundary, but still the boundary is linear. So finally, for any pi k without this assumption, this boundary is linear. So that's why this is called linear discriminant analysis. Yep. Any questions? And this is one example of linear discriminant analysis. So we have two predictors, x1 and x2. And three groups, the yellow, green, and blue. And the ellipse. So these ellipses are just the contour plots of the groups. So just the variance matrix. So this, in this case, x1 and x2 are correlated. And yes, but these three have the same variance. So contour plots have the same shape. Maybe three centers are here, here, and here. Slightly off. Yep. Then based on this, actually that we can get the boundary. And sorry, what's the boundary? The dashed line represents the true optimal boundary. So this is a simulated result. So dashed line is the true boundary. And the solid line is, I think the estimated one. It's an estimated boundary. So estimated one is kind of close to the dashed line. So yes. So this is the based on the observations of these, the squares. Yeah. So yeah, it sounds, so it separates three groups reasonably, in a reasonably good way. Yeah, so this is linear discriminant analysis. And I think that today's quizzes, we have so today's quiz, I think that we have some question about the calculating the base probability and also what, yeah, at least that question. And yeah. And now we go to, do you have any questions so far? So if not, we go to the next one. So evaluating classification performance. So we classify, for example, observations into two groups, the malignant and the benign, or positive and the negative. And suppose that there are 10,000 people for two classes. And in this example, the default and not in default. And the estimated classification rule, the misclassified only 275 out of the 10,000 people. Sorry, this is a little bit confusing. So misclassified, correct? Misclassified, yes, misclassified only. So error rate is 2.75%, 275 over 10,000, so 2.75%. And is it low or is it high in general? What do you think? Of course, it depends on the context. But, if you randomly assign the class, maybe 50% correct, 50% incorrect. So 2.75% error is pretty good. That is, initial feeling. But actually, it is not necessarily true. So yeah, so this is a little confusing, but yeah. So it's not necessarily true because of this. So we have a table, contingency table, confusion matrix of predicted class and a true class. And in this data set, actually the only 333 people defaulted. And the other 9,667 people are not in default. So that means if we predict everyone is not in default, still it's 96.67% correct. So 96.67%, this is the baseline for this data set. Right? So this is the same thing as the, making a guess. For example, here we have 10 students, and I guess that all of you have eaten at least one piece of pizza in your life. Okay. And probably it's right? So, and I'm 100% correct, but that's easy, right? So that if I make a mistake of 2.75%, that is pretty large error. So that we have a baseline based on the data set, and here the baseline is 96.67%. So error of 2.75%, still, it's smaller than 3.33%. So it's a kind of reasonable, but not, fantastic. Yeah, so that is what that is observed in reality. And another thing is slightly different, but if you make some prediction model using 10,000 observations, and you classified that 10,000 observations pretty well. But that does not mean when new data arrive, your prediction is good. So it's not really implies that. So sometimes the training error is small. The given 10,000 data sets, you can explain this is the reason that these observations are positive, these observations are negative, or default and not in default. But for new observations, test data set, often the performance is much worse. So this is overfitting problem. So that is also possible problem. Yeah. But okay, so just given limitation, still that we want to use this contingency table to describe how accurate it is. Yeah, so we introduced several measures. So this accuracy, the error rate only uses just the ratio of the diagonal part to the entire amount. Right? So correct rate is 9644 plus 81 over 10,000. So this is just the accuracy. And error rate is 1 minus accuracy. But we have to have the other criterion to, evaluate the situation, because the baseline is different depending on the data. Okay, so at first we define several things. So last time in the previous example, the most observations are true negative. Yeah, so here the negative and the positive are used. So this is obviously these come from the diagnostic medicine. So we do some medical tests that some people are positive, some people are negative. And we say that this as true negative if the true class is negative and the predicted class is negative. That makes sense. True class is negative, but actually we got the positive. Then we say this as false positive. If it's positive, but it's false. And also the false negative. So even if true class is positive, the test result is negative. That is a problem. So for example, if we consider COVID, if people who are infected are diagnosed as negative, that's a problem, and they can spread the disease more. So that is false negative. That is usually a large problem. And true positive. Actually, they have disease and they test positive. So this is a kind of test, and this is disease or something. Yeah. Yeah, and okay, so we define these four. Then, okay, so this is the same table. Then first we want to define sensitivity. That is true positive rate, TP over P. So TP over P is what? The TP is here, true positive. So true positive over this positive. So out of all, malignant patients, how many of them are test positive? So that is the sensitivity, true positive rate. So if sensitivity is 95%, basically we can detect 95% of malignant patients correctly. So suppose without prescription, those people die, then 95% of people will be saved. 5% we lose. And specificity, Tn over n. So true negative over negative. So out of all benign patients, how many patients are diagnosed as negative? So if we made a mistake, then maybe we prescribe drugs for nothing. So we lose the money for drug. So it costs some specificity. But specificity sometimes may not have to be very low, maybe 50%, 60%. Still, sometimes fine if prescription is cheap. And type 1 error is 1 minus specificity. So that is FP over N. So false positive. False positive rate, that is FP over N. Yeah, I think in this context it's a little different, but yes, the false positive rate. So the false positive, so even if the truth is negative, so the benign, still that we diagnose this as positive. So that is the type 1 error. And the type 2 error, so type 1 error is here. And the type 2 error is the 1 minus sensitivity. So even if the patient is malignant, still we diagnose that patient as the negative. So that is the type 2 error. Yeah, so in this context, type 2 error is more serious, but in statistics context, the null hypothesis is basically null, so nothing. And the non-null hypothesis is some significant, very strong hypothesis. So the false positive is a bigger problem. So this is a stronger statement, and we make a strong statement by mistake. So that is a problem. So in statistics context, actually type 1 error is usually more serious, but in this context, the positive negative context, maybe type 2 error is more problematic. Yeah, so in the previous example here, the type sensitivity is 81 over 333. So out of these default people, 81 out of 333 people are identified. So this is about maybe 30%, maybe 20, I don't know, 24%, 26%. Yeah. And specificity is this. So out of no default people, the 9,644 people are identified correctly. So actually, this is pretty high. Only 23 people are lost. So only 0.2% are lost. So if the people are diagnosed as tested, judged it as non-default, no default people, then actually that is almost always correct. And type 1 error is 0.02. So no default. So people will not default. That is predicted as default. That is a huge loss for consumer. So only 23 people, only 0.2% error about. And the type 2 error is here, 250 over 300.
Dr. Shinki, could you go back to the previous slide for a second?
Yeah, sure.
Sensitivity is a TP over P. Go to another page. Yeah, go down now.
Yeah, it's confusing, but yeah.
Sensitivity is TP over P.
Yes.
Is that the same? Is P33333?
So sensitivity and the specificity?
Yeah, is that the right one for sensitivity?
Yeah, so 81. So okay, so maybe we have to define which is positive and which is negative first. So
okay, maybe
we
that's the
have
problem.
the default as positive and no default as negative. And no default negative,
okay.
positive. So yeah. So this is the true positive. And this is false negative. And this is the total positive. So TP over P is the sensitivity.
Thank you, that helped.
Yeah. Yeah, so we have some symmetry. So it depends on how to define positive and negative. Yeah, okay, so maybe we stop here and the next time we discuss ROC curve.